All right, guys. So what we're doing today is beautiful computer science, and that might sound like a little weird. Like, why is computer science beautiful? Like, it seems like a not the right word to describe computing most of the time. But there is, in fact, a program at Berkeley called the Beauty and Joy of Computing, and this program here has been replicated around the country. Uh, Seaside One being part of it, at least. I didn't take the whole curriculum, but I took bits and pieces of it. And one of the things that stuck out to me was the notion of beautiful computer science, how you can have an algorithm that is beautiful, how you can have, in this case, we're actually going to be doing artwork with computer science. But sometimes you just find like a solution that is so elegant that you're just like, oh, that's a really beautiful solution. And what we're going to be talking about today is fractals. And if you've seen Frozen, you might have heard Elsa and Let It Go say that her soul is spiraling in frozen fractals all around. And that's what we're talking about today. So, a fractal is a self-similar art, let's say. And so, this is actually used in real life applications, not just for like cool art. Some things exhibit this self-similarity principle in real life and in computer science. So like you zoom in on like a grain of sand and it looks kind of like a pebble, and then a pebble kind of looks like a boulder, and a boulder kind of looks like a mountain. And so when you zoom in, you zoom out, it still kind of looks similar. Now some grains of sand look like crazy like crystals and things like that, but this is an example of like the self-similarity principle in real life. Some people say the universe looks like an atom, right? And so maybe we're all living, our whole universe here with all of this beautiful space around us is actually just contained inside of a single atom of like some greater universe or something like that. That's the kind of thing that my friends would say when they would smoke pot and go camping. So have you ever wondered, man, like our whole universe was just an atom? So, uh, self similarity also applies to algorithms, to programs you write. A lot of problems can be solved by breaking it down into smaller problems. And this is actually like one of those principles that, like, even if you're not a computer science major, this is something you should like learn and internalize. So, everybody's going to be solving problems in real life. And sometimes problems seem insurmountable. Like they just seem like it's just too much. And so, what you need to do in those circumstances is figure out a way of breaking down these huge, insurmountable problems into something that's workable, right? Into smaller pieces. And sometimes those smaller pieces actually resemble the bigger problem. For example, if I asked you to shuffle a deck of cards, um, it's really 5'9". If I asked you to shuffle a deck of cards, then I could hand half the deck to somebody and half the deck to somebody else and have them shuffle it however they want. And then when I get it back, I could do like a riffle sort where like some of them go on top and some go below, things like that. And then I'd end up with a reasonably shuffled deck. Well, then how do they shuffle it? Well, they could hand half to one person and half to another person and have them shuffle it however they want. And then when they get it back, they could do a riffle sort as well. And then, well, how do those people do it? Well, they could hand half to another. And eventually you're going to have to stop because you can't just like cutting in half and handing it to another person and cutting in half and handing it to another person. 52 cards, 26, 26, 13, 13, 6 and 7, 3 and 3, 1 and 2, 1 and 1. You got to stop. Okay. And that stopping point is called the base case. And in a fractal, the base case is your starting point, not your stopping point. But in this case, like a line, you just start with a line. But it's the same notion. Like what is the end line? Like what's what's our end game here, right? And so, unless you die before that without coffee, you want me to bring you a coffee, Lewis? I got a spare coffee at my house right now. So, so you have the base case that stops it from running infinitely. And then you've got the inductive step. And that's, for example, let's say you've got all the way down to the base case. You got one card and one card. And then when you put it together, you can either put the one card on top or the one card on bottom randomly. That's the inductive step. And then after you have two cards, you put them either randomly on top or randomly on the bottom or riffled between each other like that. And then when you have 4 and 4, you can riffle them together however you want. And by the time you get up to the top, you're going to end up with a deck of cards that's reasonably, not perfectly shuffled, but like reasonably well shuffled. Okay. You guys understand? So the inductive step is what you do at every level of iteration other than the basic one. Okay. And you can be surprised at how beautiful these algorithms can be. You can have a very simple base case. You can have a very simple inductive step and have a program that can sort anything, right? Any numbers, let's say. I hand you 1,000,000 numbers. You can write a program, very, very small program, that would just say, hey, sort the left side, sort the right side, and then when I get these sorted results back together, I'm going to just put them in sorted order. So if I get back 1, 2, 4 on one side, and 1, 2, 4, and then 3, 5, 6 on the other, then I put them together in 1, 2, 3, 4, 5, 6. And at each level of analysis, you sort the left, you sort the right, and you sort of zipper merge them together, like on a street where they're all kept in sorted order. And this algorithm is like 4 or 5 lines of code. It's not long. You just say sort the left, sort the right, recursively, like you have a function call itself. And then after the left side sorted and the right side sorted, you just say, all right, they're already sorted, so you just put them together in sorted order really easily. What's the base case? Sorting one number. Is one number sorted? Yeah. Sort the number 5. Okay. I'm done. You guys understand? Like one number is sorted. Like sort the number 5 from smallest to greatest. 5. There you go. It's sorted. So what we're going to look at here is some similar algorithms that involve artwork. So the base case for the Coach Snowflake is going to be a straight line. It doesn't have to be. We can see what happens when we have other base cases, but let's just for now start with the straight line. And here is our inductive step. And I want all of you guys to get out a pen and paper or use Microsoft Paint, or if you're on a tablet right now, to get out some sort of like finger drawing application. And I'm going to actually have you guys do some finger painting right now in a college class to understand computer science, which might not be anything that you've actually done before. So what you're going to do is this. Base case is a line like this. And the inductive step, what you're going to be doing repeatedly is you are going to be cutting the line into thirds and replacing the middle third with a mountain. Coloring books, exactly. Okay. So after one step, you get this. And then you do this repeatedly. How many lines do I have here now? This is gone. How many lines do I have on the screen now? What do you guys see? How many lines do I have up there right now? 4. Yeah. I got 1 here. I got 2 here. 3 here. And 4 here. Okay. And so when I repeat, I'm going to do the same algorithm. I'm going to do the same algorithm on each of the 4 line segments. So like for this guy here, I'm going to cut out the middle third. For this guy here, I'm going to cut out the middle third and replace with a a mountain, cut out the middle third, cut out the middle third, and then now how many line segments do I have? Well, I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 now. And so now I repeat the process again, like this. Okay. And for each line segment you have, you repeat the process. So what I like for you guys to do, I'm going to give you guys 5 minutes. I'm going to pause recordings. And I would like to have you run the Coach Snowflake algorithm over and over again on your art. Okay? And it's gonna start here. This is the beginning. Then you cut the middle third out and bloop, you do that. And then for each line segment, you repeat. Okay? So for this line segment, you do that. For this line segment here, you do that. Do you guys understand? And see how many iterations of the Coach Snowflake you guys can get through, earn your participation points for the week. Okay? So I'm going to pause the recording, give you guys 5 minutes, and oh yeah, the little dashes, that's just me like just trying to show you where the beginning and ending of a line is, right? Like on this one, this line here is red just to show you like that's one line. And then you can recursively apply the algorithm to that line, right? And now every line turns into 4 lines, essentially. Okay. So 5 minutes, begin. All right, and welcome back. So got some cool tree looking stuff here. What it's going to look like is iteration 0, iteration 1, and then again we recurse. Iteration 2, iteration 3, iteration 4. Was anyone going to draw this for their for their 4th step? Probably not. If you had asked me, like, is this, imagine what it's going to do 4 steps from now, I completely would not have been able to guess this, right? You can kind of see the shape though, right? Like it's like the shape kind of is there, right? But still, really complicated curve. Like if you wanted to write a program that would like go left and up and right and left and down and up, like, man, that's a tough one. Right? Whereas the actual algorithm to make this is very simple. Take a line and replace the middle third with a mountain. That's it. That's all it is. And you could write that program, yourself in Scratch pretty easily. Guess what your next homework assignment is? Not to write it, to modify it. But yeah. Okay. So now if you have a triangle to begin with, that's why you end up getting something called the Coach Snowflake. It's the triangle is the starting point. The triangle is the base condition, and then you get this cool looking snowflake out of it. It's the same thing, just tripled basically. Okay. And then you can do the snowflake zoom like this, which has no relation to zoom calls. And I don't know if I can open that file. Let's see. Okay, sure. All right, yeah, but you can see, like, as you zoom in, you can see the self-similarity principle in action, right? Like, you can see that as this thing zooms in, you keep getting more detail, and the zoomed in level looks like the zoomed out level. Anytime you have a problem like this in real life, where a bigger problem can be broken down into a smaller program that looks the same, then oftentimes you can use a recursive algorithm where you break a problem down into subproblems that are the same, and you keep breaking it down the same and breaking it down the same and breaking it down the same until you get to the base case, which would be something like this. And then this is a very simple thing to solve, right? And this is a good lesson for real life too. In real life, you're going to be given extraordinarily complicated problems sometimes. And we could be talking about things not like, homework, but like, your car is broken down, you're late for work, your kid's sick, and you got to call the school, and there's like 900 different things that are all going on at the same time. And you have to learn how to break it down into manageable chunks and figure out what you can do now, what you can put off, who you need to call first. All this kind of stuff is important to like just being a successful person in life. And I don't consider being successful being like an Elon Musk or Bill Gates or something like that. I consider somebody successful as like when they have basically accomplished what they want in life, and that varies from person to person, right? But if somebody wants to become a journalist and they become a journalist, right, at the level they want to be, like they want to be a newspaper journalist or they want to be a news reporter or something like that, then that's what I consider successful. They've sort of like established reasonable goals and achieved them, and in order to do that, there's a lot of hurdles along the way that can cause you to fail. And if you don't apply to the newspaper job on time, things like that, and that's one of the reasons why I'm a stickler for deadlines in this class, is because it's a good lesson for life. If you apply a day late for your newspaper job, they're not going to hire you, like unless your dad owns the newspaper or something like that. So I go to Scratch, and you can see here that it's drawing the Coach Snowflake. Now, it's drawing it very slowly, right? And so there's a trick here. If you hold down Shift and click on the green flag, then this will turn on what's called turbo mode. And turbo mode means, let's take a look at yours. Okay. Oh, you tried. That's the important thing. All right. So turbo mode will have it draw instantly. Okay. And so if we run this, you can see instead of it taking like forever to do it, right? If we're doing this normally, you can see this thing just crawling, right? If you turn on turbo mode, then it just draws everything instantly. So whenever you guys work with fractals online, it's probably a good idea. Shift click on the green flag, and that turns turbo mode on and off. Okay. So let's do the Levy curve, and we'll spend a few minutes on this. So the Levy curve is very similar to the Coach Snowflake, except instead of just the middle third turning into a mountain, the whole line does. So it's even simpler. You're just going to have 2 lines instead of 4, like the previous one. You started off with 1 line, and then you got 4 lines, and the 4 lines turned into 16 lines, and 16 lines turned into 64 lines, and 64 lines turned into 256 lines, and 256 lines turned into 1,024 lines, and 1,024 lines turned into 4096 lines, etc., etc. This one, it's doubling every time. So it goes 2, 4, 8, 16, 32, 64, 128, 256, 5, 12, 10, 24, 20, 48, 40, 96, etc., etc. It's easier to manage, right? And so basically just take any line segment you see here, and that is too funny. That is great. That is beautiful. So for every line, just replace it with 2 lines at a 90-degree angle. Okay? So I'll give you guys 4 minutes to work on this. Begin. So the Levy curve really threw me for a loop the first time I saw it. So I'm like, all right, I kind of understand this. We go from here to here. All right. And then for the next one, I was kind of imagining like a mountain kind of like sticking this way and a mountain sticking this way. But it actually turns into a 3-sided rectangle, I guess. That's one way of putting it. And so I'm like, okay, I kind of get that. And then for the next one, it's like, okay, yeah, I can see that. All right, sure. Now, then I ask myself, what's it going to look like after you do this 12 times? Okay. And you get a gold star. So that's kind of what I had in mind, right? I kind of figured it'd be something like that, right? And what you actually get after 12 iterations of the Levy curve is this, which I did not see coming. This is an immensely complicated curve. Like if you're trying to program this just by hand, like go down, go up, go down, go up, like what, and this is not at all what I would have thought this would turn into, because this is simpler than the Coach Snowflake, right? Like the Coach Snowflake is doing four segments, right? And this is just two, and you end up getting this thing, which is like wild, right? So Taj, all right, cool. Yours is wrong. Yeah, I figured. Me too. Like, don't beat yourself up. I'm just, this is why, we do class participation. It's not class getting it right. It's class participation. So that's it's an interesting geometric pattern, I guess. Interesting. Yeah, I like that one. I mean, it's wrong, but it's really cool. I like it a lot. Huh. Weird. Okay. So, what you're going to do for your homework assignment is you are going to find a fractal. Yeah, we'll save that. You're going to find a fractal, and I've posted it on Canvas. This assignment's called Frozen Fractals All Around. I can let it go. Right? And so I've posted various fractals in Scratch. So, for example, here is a thing that will draw like a fern kind of thing. Kind of cool looking. Click on the See Inside button there, and you can see that these fractals are usually not that complicated. Like, this is probably less code than your story, right? This is actually like a page or two of text. And what you can do is, what you're going to do actually is you're just going to mess with them a little bit, right? It's like maybe you're going to change, one of these numbers from a 0.85 to a 0.55, and change this one from a 0.28 to a 0.88, and this one from a 0.26 to a 0.16. I don't know. And then when you hit run, you can see that the thing starts changing. And we can set this to, I don't know, 0.55, and this one to 0.14. And you just sit there and just mess with the code. You'll see that it actually 9. Like, as I change it, because I'm running it right now, right? You can actually see the fern like change in real time. And so you're just going to mess with the numbers. Like, you don't have to write a fractal program from scratch. You can if you want. If you want extra credit, you can write one of these things from scratch. But the idea of this is just to let you guys understand that a big part of computer science is plagiarism. Is taking other people's work and calling it your own. Is taking an existing program and tweaking it and modifying it and making it your own, which is called plagiarism. Wait, no. You understand, let me put it, seriously. One of the best ways to learn computer science is to look at somebody who's done something already similar to what you've done. And so if you can find source code for somebody who's made some sort of multiplayer trivia game, right? And you're going to be doing you've been hired by Jeopardy to make Jeopardy online. You find somebody who's done some sort of server and client communication things. You look at it and you see how they do it and you understand it. Having examples to work from is incredibly useful. A lot of times I don't understand the documentation because the documentation is very big and hard to understand. So you find an existing program that kind of does something similar to what you want, and then you start messing with it like this, right? And so I could just change one of these values here to 0.99, and you can see the thing reacts in real time to this, right? 0.14, negative 0.14, and then I can try it again. And you can see that as I just mess with these values, this thing, mutates. And I want you to come up with something cool. I want you to come up with a new fractal of your own. I don't want something boring. And for the homework assignment, you're actually going to post the original, and then you're going to post yours. And it has to be substantially different. Not completely new, but just different, like this, right? I don't want you to be I changed it from 0.85 to 0.86 and I'm done. No, you're not getting 10 points for that. You need to mess with it. You need to understand the spirit of play in computer science. You take something, you manipulate it, you adjust it, you see what happens. That sense of experimentation and play, and in this case, you can actually visually see the outcome. That is one of the most crucial skills in computer science: the ability to just mess with something and see what the outcome is, and develop an understanding of it through play, through messing with it, through changing it, through modifying it. Like, if you're interested in making video games, then one of the best ways of learning how to make video games is to modify video games. Because when you're starting off, you don't have enough skill to make a game from scratch, right? Here's a blank page. Go make World of Warcraft. No, it's not going to happen. But if you find source code to a game that you like, then you can sit there and be like, okay, I'm going to add a new weapon to it. I'm going to add a new monster to it. I like this Minecraft game. I'm going to go add, some new, flying whale or something to the game, right? And the more you spend messing with it and modifying it and tweaking it, the more you understand how this big, complicated thing works. And that's actually a great way of learning it. It's kind of like learning it from the inside instead of somebody from on high kind of giving you a lecture. Like, by just sitting there and playing with it, you come to understand it. And that's how I came to learn Quake. One of my things I'm most famous for doing is making a Quake mod for Team Fortress called Custom Team Fortress, which allows you to build your own class, right? So you can take a sniper and mix it with the medic or whatever, and you got a budget, and so like it's not unbalanced, and you can sit there and play with it. And I learned how to do that because I made multiple mods over and over again. But I learned how everything worked by just sitting there and doing it from the inside. Instead of creating a brand new game from scratch, I learned how it worked by changing things. And I would just start by just changing a little thing. Then I'd change a bigger thing and see if I can get that to work. And by the end of it, I had a pretty good system mastery of the whole thing because I'd been messing with all the different pieces for so long that I came to understand how the engine worked overall. So, plagiarism. I'm not plagiarizing, I'm learning. Exactly. Yeah, just don't use ChatGPT to do this. Okay. So that's amazing. Yeah, it's called it's not plagiarizing when it's within the bounds of ethical behavior, I guess. I don't know. But yeah, it's called modding, right? So you mod a game. Okay. So that's what you're going to be doing. Your homework assignment is going to be modding a Fractal program. And I posted lots of Fractals on here. And just find one that you like, mod it, and then you're going to submit the original. You're going to submit your change. You're going to explain what you did. And if you want a challenge, write one from scratch, I guess. All right, so that's it for today, guys. Hope you guys can see that computer science has some really cool, very simple things can turn into very complex and very beautiful things on the back end. So I will see you guys on Monday. Peace. Happy 4th of July.